Okay, so this is in case you missed in class last time, me going over that last bit of the podcast at the bottom of page 9, and then the two problems on page 10. So this is that page, at page 9 at the very bottom, where I asked you to finish out this problem. Notice this is limiting reactants because I have two separate givens, 5 moles of iron and 6 moles of oxygen. And that means we're going to have to work two separate problems. So when we set that up, we're going to start with one of our givens, and in the podcast I set all of this up for you using that mole ratio and then getting to grams of that iron oxide. If I stop and calculate this, that number is 399. And then I do have to do another problem with that second given. But even though it feels like a whole nother problem, it's going to look basically the same as the first one I did. It's just that everything that I previously had that had iron in it is going to be oxygen instead. But everything else is going to be the same because we're still trying to figure out how much of that product we're making just from this other ingredient. So if oxygen's going on the bottom, then this time I'm going to be using those 3 moles of oxygen from our balanced equation, still putting the 2 moles of iron oxide on top, but it still asks for mass, so I'm still going to have to use this exact same molar mass as what I did in that top half. When we multiply across the top and divide across the bottom, that gets us 639 as our answer. Now remember, we're not using both of these as our answers, so we always choose the smaller one. With 2 givens, we work 2 problems and choose the smaller one. So 399 is my actual answer, getting my units and that substance on there to make that full and complete. So this is our answer to part A. Then it asks us to find I changed that to moles, of the excess reactant remaining after the reaction. And this is the part that some people struggle on mentally to remember how to do what they need to do. So if we focus on what we're talking about here, it doesn't ask us what is limiting and what is excess, but you remember the reactant, one of these things, the one that is limiting us is the one that makes less. So the one that made this smaller number was our Fe. So Fe is our limiting reactant, and that means that oxygen is what we call the excess reactant. So in this part B, where it says to find the moles of the excess reactant, I'm trying to find moles of oxygen that's left over after the reaction. And I can find out how much is left over because that's going to take how much I had, or maybe how much I was given to work with, and then I have to subtract how much got used up. So I'm trying to find how much is left over. I know how much was given because it told me that was my 6 moles. Now I just need to calculate and figure out how much was used in order to make this stuff. So because that's the stuff that I'm making, that's going to be what I use as my given in this last stoichiometry problem. I'm going to start from the real true answer, these grams of iron oxide, and I'm going to work backwards I'm going to work towards getting moles of oxygen. And I keep saying it's backwards because it is literally this problem working backwards. I'm going to first thing have to cancel out these grams of iron oxide and get moles. So I'm going to be using this down here, just with that 159 number on the bottom and the 1 mole on top. And then I'm going to have to change my moles of iron oxide to moles of oxygen using this same ratio. It's just going to be backwards. So you can imagine it as a completely separate problem, and it technically is, but is using all the same numbers that we've already used before. So I already kind of told you what I was planning to do, so let's do it. First thing first, cancel out those grams by putting the molar mass of that thing on the bottom. Opposite side of our grams is always 1 mole, grams per mole. Now that I have moles, I can use my mole ratio. I'm trying to find moles of oxygen, so that's going to be a 2-to-3 ratio. The 2 part goes on the bottom because I need iron oxide on the bottom to match these iron oxide moles on top. And then I have to put the oxygen on top. So like I said, this problem right here, every single bit of this matches every single bit of this. It's just backwards. So I know it seems like a lot for a single question to make you do 3 separate calculations, but it's really just kind of like one problem and then 2 half problems after it, because most of these numbers are getting used over and over again. So this gives me 3.75 moles as my answer, and I like to write that that's how much got used. That's how much oxygen I needed to make this 399 grams of iron oxide. Oh, look at that. Okay, well, that's gone. So this is how much oxygen got used, and over here, that's 6 moles of oxygen is what we were given to start with. And so I'm going to do a real quick subtraction and take how much I started with minus how much I used. So 6 minus 3.75 tells me that I have 2.25 moles left over, 2.25 moles of oxygen excess. So that is my answer to part B. So the gist here with being able to find how much excess we've got is to take the answer to that first part, use it as your given, and work to find how much of that excess reactant we are going to have used, and subtract to figure out how much excess is left over. So I know it's a little bit weird, but if we look at the next page when we're working this problem at the top of page 10, you'll notice this one doesn't ask us to figure out how much is excess. This is just a limiting reactant problem with 2 givens, so I'm just going to be working out 2 problems. So even though that part is a little bit hard, a little bit tricky, it's not always going to get asked. We don't always ask you to do everything that you should be able to do. And sometimes we just ask you for one part. If you look at the next question, sometimes we ask you for 4 parts, but we'll get there. We'll handle it. So I see 2 givens. The difference about these givens is that they're grams. And I'm looking for grams of my gas that are being produced. So just kind of thinking about this, I have 16.2 grams of aluminum going in and 61 grams of HCl going in. And which one of my products is going to be a gas? Well, you might not remember, but hydrogen is a gas. It's one of the smallest, lightest molecules, easiest to be a gas. So we're trying to find out how much hydrogen we're going to make in grams. So I'm got 2 givens, working 2 problems, making sure we get grams out at the end, and make sure we choose the smaller answer as our real answer. So I'm just going to start with that first given, that's 16.2 grams of aluminum. If I have grams on top, I'm going to put grams on the bottom, 1 mole over that. I'm trying to turn this aluminum into hydrogen. So looking at my balanced equation, that's a 2-to-3 ratio. So I'm putting those 2 moles on bottom and 3 moles on top. But I need grams of this hydrogen gas that is being produced. So I'm going to use the molar mass of hydrogen, just putting the 1 mole part on bottom so I can get those grams on top like I wanted. So multiplying across the top and dividing across the bottom gets us 1.82. Might be my answer, might not. Have to work this second problem before I know. 61 grams of HCl is my other given. Just like this first problem, even though it is a completely different substance, my setup here is going to match what I was doing here. So I'm going to be putting the molar mass of HCl down here. I have to add up my H's and my Cl's, but that goes on bottom, 1 mole on top. This next bracket here is going to be the same type of thing I did here, mole ratio. It's just that instead of Al, I'm going to be putting HCl's number on bottom, but I'm still trying to find hydrogen gas. So 6 moles of HCl on the bottom, 3 moles H2 on top. And then this last bracket is going to look exactly like this one, because at this point I've got the same substance and I'm still wanting to find grams of that substance. So even though it is a long problem and we've got to work 2 of them, they're not completely new problems. So this is set up, multiply and divide, and this gets us 1.69. Smaller answer is my real answer, so 1.69 grams of hydrogen is the answer to this question, and that's all it asked for. So we're done. Hopefully this process isn't too scary. I know it's 2 problems, and that's the last thing that you want to do with stoichiometry, but hopefully it's helping reinforce the process that we're doing. So one last problem, I can't exactly work this one out this way because I don't have enough space on this screen. So hopefully I can write clearly enough. So this first step, I don't know what else to do other than balance my reaction. Then I'll start looking at everything else. So this is going to be 2, 2, 2, 1 once it's balanced. And as I'm kind of thinking through things, it tells me that I have, I'm going to change colors here because I don't have much else going on. I have 40 grams of sodium reacting with 36 grams of water, and we're trying to figure out how much hydrogen gas is being created, but I do want that to be in grams. So this is another gram to gram problem, trying to find grams of my product. 2 givens is going to be 2 problems. This is going to have a lot of more steps following after it, starting with finding the limiting reactant, then doing that kind of backwards bit where we find out how much is left over, and then it asks us to find percent yield. This is what we call a super stoich problem because this one question, manages to cover every single thing that we have done in this entire unit. You're going to have one of these on the test, and it's going to be all of these parts, and it's going to start by asking you to write out this reaction. So it'll tell you, like, sodium and water react to form sodium hydroxide and hydrogen. A step is going to be write and balance the equation, and then B is going to be calculate how much hydrogen is produced, so on and so forth. So you need to be able to do all of this stuff together, but don't let that scare you. Every question on the test isn't going to be a 5-part question. It's just that one last part. So you'll have plenty of simple questions where you just work one thing, do it, done, and then there's going to be one of these. So first step is going from grams to grams of each of these givens. So I'm going to try and leave myself as much space as possible as I set these up. Let me see if I can set this up nicely. Okay, so I think these lines are straight enough for me to work with. I've got both of them set up to make sure I have enough space for both of them and the other parts that I'm going to be doing. So starting with this first one, I've got grams of Na on top. So I'm going to put these grams of Na, the molar mass from the periodic table on bottom, and 1 mole goes on the opposite side. Now that I've got moles, it's time to do my mole ratio. So my Na to my H2 is going to be a 2-to-1 ratio. So I'm going to put those 2 moles of Na on bottom, 1 mole of H2 on top. But it wants us to find mass, and luckily, just like the last problem, H2 has the same mass of 2.016 grams of hydrogen. So I didn't even need my line to be quite that long. Yay! I'm actually going to set up this next one first, and then I'll find both of these calculations. Just want to keep going while I'm on a roll. So just like above, I'm putting my molar mass on bottom. This time it's my molar mass of water. It goes on bottom, 1 mole on top. And my mole ratio to get from water to hydrogen is actually the same, 2-to-1 ratio. So 2 moles on the bottom again, it's just water. 1 mole of H2 on top, but I want mass of H2. So we have to change those moles to mass by using that molar mass again. And here we go. Both of my problems set up. Now if I stop and calculate them, these are my 2 answers I get out, and the smaller one is my real answer. So there's that 1.75 grams of H2. And that is my answer to part A. Part B is actually not a very long question. It just asks you to identify the limiting reactant, and the limiting reactant is the one that makes less. So it's the reactant that got me this lower answer. So if I just follow that back to the beginning, then that's Na. Might be hard for me to squeeze that in here, so I could just say that Na is my limiting reactant here, but that is kind of hidden, so I'm just going to write it here. Limiting reactant equals sodium. And that is my answer to part B. moving right along. Part C asks us to calculate the mass of the excess reactant that remains. So if sodium was our limiting reactant, that must mean that this water was my excess reactant. So I'm trying to find the mass, the grams of water that were left over. And in order to find my leftovers, I need to know how much I'm starting with. So that's right here. It's a little hard to see through. And then I'm going to subtract how much I used. And in order to find how much I used, I have to figure out how much water got used to make this 1.75 grams of hydrogen. So I'm starting from my answer, working backwards, canceling out those grams of hydrogen, turning it into moles so that we can use our mole ratio. And this had 1 mole of hydrogen to 2 moles of water. I'm going to water because that was my excess reactant, but I need grams of excess to compare to the grams that I started with. So I'm going to finish out by using the molar mass of water. So this is going to tell me that this question or this problem needed 31.3 grams of water to get used to make all of that hydrogen gas that we found before. But that's how much we used. We started with 36 grams. So we need to real quick do a little subtraction here. I'm going to change colors because I'm running out of space. Just trying to make this stand out. So 36 minus 31.3 tells me that I had, what is that, 4.7 grams of H2O that was excess or left over. Having to go off of my page just to try and get it to fit. Okay, so that is my answer to part C. And I'm going to have to do all of D in the margins. Hopefully you have a little more space than I do, or maybe you write a little smaller. But part D asks us to find the percent yield of hydrogen if 1.52 grams of hydrogen was actually produced. So as soon as I see that percent yield, I should be thinking of my percent yield equation. And my percent yield is my actual divided by theoretical times 100. And it told me my actual in this problem, and it really wanted me to know it was the actual because it said the word actually there. So 1.52 is how many grams of hydrogen I actually produced. I just need to figure out what my theoretical yield of hydrogen is. And I've got a whole lot of numbers here, but there was only one number that was grams of hydrogen. And that's my theoretical yield, how much I should have made. So that's 1.75 going on the bottom. And then, of course, times 100. And when I do that division, we get 86.85, which is going to round to 86.9% as my percent yield and my answer to the final part of this question. So this, I know, is a kind of a mess, but this is how we work out these problems. I know that it's a lot of steps, but each individual part isn't that bad. Just part 1, we work 2 problems. The second part B, we have to look back at the beginning of those problems. C, we need to do one more problem, kind of like one of the ones we already did, just backwards. And then D is just some quick division with all these numbers that we already have. And if we're careful about labeling our numbers and how we use them, then it's easy to go back and find the numbers that we need. So I know I just said it's easy. It's not necessarily easy. Each step of this shouldn't be too hard, but I know with stoichiometry, the biggest struggle is what do I do next? Because each problem is going to be just a little bit different in how you set it up and work it out. So take it slow, take it easy, find the parts that you can do. If we look in our packet, the next pages, when I want you to be working on, break it down into those similar 4 parts. This one does have you write out and balance that equation. Make sure that you're remembering to check your diatomics when we have these elements alone. And iron 3 chloride is made when iron has a +3 charge and gets together with chlorine, which has a -1 charge. So be careful writing out that equation. Make sure it's written and balanced correctly before you start your stoichiometry, or else all that stoichiometry is going to be wrong too. I also suggest, this is one of those limiting reactant problems. We are going to be having to do 2 problems with these 2 givens, but the amount of space that they gave you in part B is not very much. So my suggestion is work one of your problems here and one of your problems here. And once you get those 2 answers out, that's going to help you answer which one is the limiting reactant. So just come back to the beginning and label it once you work those out. So that'll give you a little bit more space to do it instead of shoving them all in that same space for part B. So we've got those multi-step problems, those super stoich problems going on there. Got 2 of them here on page 11, another one on page 12, and then there's a couple of problems that aren't, 4 or 5 steps long. So if these multi-step problems are too intimidating, come and try and work one of these problems at the very, very end. Or maybe just do part of it, write that equation, or just do the limiting reactant part. If you're struggling on finding how much excess is left over, do everything but that, and then I can help you in class at how to work out that problem. But today was really one of our last days to work on things in class. Next class we're doing a big old lab, and then we have a review day. And we'll have a little bit of time to be working some problems in our packet on that day. That's also when we're doing s'mores. I also have some more review problems to help you with. So we need to try and get this packet as finished as we can at this point. Okay? Let me know if you have any questions or need me to check anything.